Hi everyone, welcome back to Becoming a ROS Developer, the YouTube channel from the Construct. My name is Rodrigo, and today we're going to be looking at a course presentation for one of our courses for ROS Navigation in 5 days. So we have our student Mike here today who's going to show us what he did with this final project for this course. So hello Mike, how are you?
Oh, hey, I'm good, thanks.
Great. So yeah, whenever you want, you can start presenting what you did. You can share your screen and then just go ahead and tell us what you did.
All right. So I've had a couple of issues with latency and stuff in the past. So I'm gonna do like a abridged version of my PowerPoint presentation and then go into some of the coding that I did, and then maybe show if there's enough time, show some raw footage or some live footage. But yeah, that's kind of the setup, and let's hope that this presentation goes well.
Okay.
Um, and I'm even having trouble getting this. Okay. All right. Let me just make sure that I can. Okay. So, um, yeah, my name is Michael Rizzo. This is my navigation project for the construct. So in this course, we focused on learning more about the ROS navigation stack. This was broken up into the mapping, the localization, and the path planning module or
Mm-hmm.
modules or nodes. And um, each of these nodes has like certain inputs, outputs, and we kind of had to go through and focus on tuning some of the parameters and doing a lot of the integration among the nodes and things like that. So like for like the basic course structure, we would just like go through these notebooks and do some in-class exercises, and then we focused on doing this final project. And for me, this was really just to get better accustomed towards more advanced robotic algorithms, and to sort of build a little bit on the prior work I did in the basics course. And yeah, so for the final project here, we kind of just focused on getting the robot to move around the closed track, and the main objective was like to get the robot to visit like these key points, like the corner one in the top of the map here, and then corner two down here, and then pedestrian or like right in front of the crosswalk.
Mm.
And like I said before, like this was done via like going like doing like a structured going through setting up the mapping behavior, the localization behavior, and the path planning behavior. And like the mapping behavior, you kind of had to go through and start the SlamG mapping node, and then once you started that, that would like read from the laser data, and it would build an occupancy or a grid map and kind of stuff like that. And so basically, in order to do this, I would go onto the online environment. I would
Mm-hmm.
go through. I would like use mainly use the IDE to code up to do some of the coding, and go back to the web shell, start up like the gazebo environment, then start the various nodes and like do some my debugging in the simulations. And then finally, once I kind of got things up and running in the simulations, I would go to the set up a session to go to the lab, and I would record some of the behavior and then go back and analyze and maybe iterate again, or just stop and then contact you guys. But this was some of the results that I had gotten. This is for the corner one on the left, and then for on the left is the simulation, and on the right is the lab environment.
Mm-hmm.
And you can see in this that it does pretty well in terms of what it should do. And there are some discrepancies where, like for example, it backed up a little bit. And generally though, there was a pretty consistent correspondence. This is for the pedestrian case where you had to come in and go and stop right in front of the crosswalk. And you can notice here it's pretty well, it shows again. And there's some discrepancy again in terms of like it's not really that close, and that's kind of it translated both from the simulation and the environment, but kind of the gross behavior was there.
Mm-hmm.
And again, this is for corner two. You can see in the lab environment, it goes generally to where it should. And then for me, this was just kind of a homage to the first project, where we did the lap, and it wasn't specified, but I just wanted to see if the robot could do it. And so I kind of set things up where this was like showing in the simulation, and then here I told it to go from corner two to the pedestrian, and now it's going to start doing the lapping. So it does it pretty well again. I mean, this was another thing. Like at the beginning, we saw the pedestrian, like it returning from corner two, it kind of overshot its mark a little bit, and then it did go back and return to its goal. And I did notice like various occasions there was some artifacts in the recording, so I kind of had to edit things a little bit. But
Mm-hmm.
generally, things were pretty straightforward, and you could see that the robot, again, it does the entire lap and it stops where it started. So some of my conclusions for this course was that it was a lot. It was straightforward, but it was a lot, and I don't really appreciate as much as I'd like to many of the parameters that are involved. And I mean, there's like 50 parameters per node, and I really like to get a better grasp of some of that stuff. And as I had mentioned when we were looking at some of the footage,
Mm-hmm.
that the robot does manage to do all of its tasks as specified, but there were a lot of notable errors like that I was encountering, like some of the trajectories, at least to me, they weren't really that common sense. Like they were kind of awkward. They like if I increased the goal tolerance, for example, it would kind of oscillate a little bit, or occasionally it would go like some random location. And the collision avoidance was an issue more so actually in the simulation, because the simulation had much more obstacles. And I noticed, for example, that if the inflation radius was kind of like iffy, like it was too much, or like my kinematic parameters were too high, that the robot would like overshoot a lot and kind of it would get stuck, unable to like find the right trajectory and things like that. But um, after I tuned it enough, I could get it to work. It was just kind of really a lot of like patience and tuning of parameters, and then
Yes.
occasionally there was some issues where it just went off to some random location or didn't even find its goal. And so like all that considered, I'd like to become more adept at understanding some of the algorithms in Slam, and being able to approach more realistic environments, and maybe going towards like something like sensor fusion, or implementing learning mechanisms or something like this. And I know that ROS offers some of those courses that I can continue to improve, and maybe some of my own research. But yeah, that was kind of like the project overview. I know it's kind of fast. If you want to see like a more detailed version, I can give you the link. But that was kind of the abridged version of the general overview of what it is I did for this course. And I guess we could look at some of the codings, because I know that that was suggested. And
Yeah. So I've been writing questions, so
okay, yeah.
I can wait until for you to be done with your whole explanation and then ask you, or I can start interrupting you, whatever you want.
Yeah. Can we just get like maybe just do the code and then
Yes,
try to give
yes.
them?
Let's do that. Let's look at
Okay,
what you
yeah.
did.
I'll just do like an abridged version of the code too. Like this is the
Perfect.
general structure where you have the mapping, localization, navigation, and path planning packages. And the navigation package specifically looks to integrate the other three packages. And so it was kind of straightforward in terms of what each package constituted, where you have, for example, the SlamG mapping launch file, which basically launches the ROS native SlamG mapping node. And really for many of these launch files, we really just had to focus on understanding a lot of the parameters. And there was some coding that we had to implement, or at least I found that I had to implement.
Mm-hmm.
And there's many different ways to go about doing any given problem. But for example, when I went for the mapping package, the specific thing that I had to modify here was the
I'm
teleop.
sorry, I can't see the code. I see the conclusion slide.
Oh, you see this? You can't see
Oh, I can
the.
see your mouse moving around now. So maybe you have two screens and I can only see one.
You can't see me showing you the code right now.
No, I can see the conclusions slide of your presentation.
Oh, yeah, I got out of. Maybe I'll stop. I'll stop my screen sharing is paused. Can you see now?
No, I still see the same slide. Maybe drag over the window on top of the conclusion slide, and maybe that will. Work?
Okay, I'll stop sharing and then I'll share
Yes. How
again.
about that? Let's do that. All right. Now we see code. Cool. We see a launch file
Okay.
now.
Yeah, so this was like the SlamG mapping launch file for the mapping package. And as I had mentioned, like the general structuring was like, okay, we have the localization, the mapping, and the path planning packages, and then the navigation package kind of integrates the three in. And from each of like the major three packages, it was basically just like us setting up parameter files for the various, like the SlamG mapping node is a ROS native node, and we just kind of had to tune some of the parameters for our particular project. So this was kind of just some, I didn't do a lot of this. I actually was able to use just what was given to us from ROS anyways, but there was
Hmm.
occasional parameters that I really had to go back and look at to further tune in, like a lot of like tolerance parameters, or a lot of like parameters related to robot kinematics, like the acceleration or velocity or whatever. And one of the things I did for the particular mapping package was I modified the teleop program a little bit, and I can show a picture of that, but like the
Hmm.
command line of that. But basically, what I ended up doing is like um, I included a save, like I on the command line. Basically, when I wanted to save like the map, I would just hit R, and then it would just save the map to a folder. And for the that was for the mapping package. And then for the localization package, if I wanted to save like a coordinate that I would send as a goal for the robot, I would go and I would, for the teleop, I would manually go in and I would hit T. So like I would do like different um, various commands for the teleop that would just allow me to manually save the map, or to manually record a point. And you can see like here is like the map folder. And I can go through some of the more, I don't really have a whole lot of time, but like it was kind of really just straightforward to um, do like a basic, just a simple map saver. And ROS has this map saver in it, and I kind of just modified that a little bit to allow it to integrate in with the Turtlebot package.
That's great.
And yeah, and this is
So
kind of
So what did you exactly do when you pressed R to save the map? Did you do like an
um,
OS? Oh yeah, or like a command outside of this, or how did you make it so it would record it? Uh
so
huh.
right so right here, yeah, I don't know if there was like a more professional way of doing it, but I just
I
I
mean,
would
this is really. I mean, usually we just use the command to save the map, but this is like a step above, which is real nice.
yeah. So I would just like, I had like a class that I created in my maps. I think that's how I did it. Like there's a map saver class, and then the map saver class just goes in and it saves a OGM file, which is kind of the OGM file, how you save the OGMs. Yeah, so I have the map generator class, and in the teleop, I just import in the map generator class, and I use its um I forget what I do exactly, but I guess it's a once I hit R, it goes in and it saves. um yeah, I can't remember exactly what it is I did, but yeah, there's a map generator class, and it goes in and it will there's like a callback for there's a subscriber object to the occupancy grid. And once that's called, it will just go in and it will save to the maps. And
Oh,
I can give a more detailed explanation of that if you need it, but like for right now,
that's
yeah,
fine.
that's
I'll ask
kind of
questions
yeah.
afterward.
Yeah. But yeah, so the AMCL is just a similar thing where you have the AMCL. The AMCL is another node in ROS, and it loads up the map that you just saved, and then you have all your arguments inside. And for this particular one and a couple of other ones, like the for the path planning, when there was a lot of parameters, I put them in their separate parameter files. And yeah, so that was for the AMCL. And for the AMCL too, we had to save the spots. And again, I don't have this memorized at the top of my head, but usually it's like I just mainly do like I'll do like a class that has various like it was a service server, and it subscribed to the AMCL pose. And When you called the service server, you had the callback for your AMCL pose here, where it was collecting in the position and the orientation data. And once you called the service server, it would basically take the collected orientation or position orientation stuff, and it would associate the orientation and position with it with a label, and it would just save that label into a YAML. And that was kind of just doing a basic OS path, or just a basic write to a file, or a YAML file.
So this
And
is what you were doing when in the demo, right? When you were sending it to locations. This is the program that it's using.
yeah, well, so when I send the demo file uses, there's the move base node, and that the demo file specifically uses the send coordinates, and the send coordinates is contained in the navigation package. The navigation package integrates all of the various all the various nodes, like the mapping node, the localization node, and the path planning node. So you have what you saw in the demo, or those demos, was the navigation package, and the navigation package contains the action client set coordinates and the service server get coordinates. And get coordinates is, so what I was just showing you there for the save spots is in the localization package, and that's just how that just identifies the key areas on the map that you want the robot to go to. And then once you have kind of identified those areas, those are all now saved in a YAML file, and then you start up the navigation package, and the navigation package will then um, um, wait and listen for the user input to see which of the areas it wants to go to. And it does that right in here. We have the send coordinates, and the send coordinates will basically, once you send in a label, like, oh, I want it to go to corner one, then the send coordinates will get the coordinates that were saved from in the YAML file, and then it will send it to the move base node. And the move base node is like, it does its thing. Like, I didn't code up anything for the move base node. It's just a ROS native package that has inbuilt functionality, and it's just a simple action server that you send, and it will transform the coordinates that you send to it into velocity commands that it sends to the base controller. And that's kind of, yeah, so that was kind of what you saw in the presentation for some of those footage. But yeah, that's kind of, so the move base node, again, is just another node where you have a bunch of configuration files that you have to go through. And I chose like this is one where it's the planner. Like, this was like one that I commonly visited because I had to really adjust some of these kinematic parameters to allow for the robot to function properly. And
What do
this
you
was
mean by that?
so um like, if you set, I don't know if it was in this particular course, but I know in the last course, for example, that the maximum velocity that we could specify for the robot was 0.3, and if it went above that, there would be like some error command that would
Oh
or some
yes, we have a
interrupt.
safety that kills, so
Yeah.
just it doesn't go that fast. Okay, I see.
And there's other nuances, like if the acceleration is too high for like the X, I would
Uh-huh.
notice that when it would go to certain places, sometimes, like if it had to turn, and the acceleration was too high, like the trajectory would like overshoot way too much, and it would just like get like a lot more like buggy in terms of like I don't know, like it would just like kind of like, if it overshoots a little too much, like maybe like the collision avoidance system would like find itself in some like terrain that's kind of like tricky to get around. So
Yeah,
you kind of have to
yeah.
like be careful.
So that's
Yeah.
that's the nature of a controller, right? So
Yeah.
that makes sense because uh, think about it as a sine wave that's going to a line, right? As time goes on. So it makes sense that with higher velocities, it will take longer for it to reach a point, a set point that you want, because it would just oscillate between them. But so yeah, that's why I was asking.
Yeah,
Okay.
yeah. Yeah, I mean that's kind of like the gist of it anyways. And I don't know if you have any questions or like I think I kind of run out of time in terms of presentation, but
Yes, I have some questions. Great job, by the way. This looks very complete, and it looks like you did what's most important with these things, which is just testing and testing and testing and testing again, especially for um, robots that you don't necessarily know the physical properties of, right? So let me ask you some questions. Well, let me tell you what I liked. I really liked what you did there for your teleop node. I know it's not part of um, the project, but I thought it was really clever for you to, I guess, save as many maps as you want, as quickly as you want, and save spots. So that shows that you can connect uh, something like this node to the system where you record the coordinates of your interest spots, let's say. So I really like that. And let me just ask you some questions about the things you said. So you talked about a difference between the simulation and the real robot when you send a goal to a spot, and in the real one it goes a little further, a little more ahead. What would explain these small differences?
um yeah, I mean it would just be me kind of guessing. Very often like when I go to the lab, like for example, one of the things that I've noticed is that parameters that are in the simulation, like if there's some threat, for example, if there's a threshold parameter and the threshold in the
Like which
simulation
one?
is set, um, I didn't really have like, oh, like for this particular example, I think something that I was noticing, for example, was like the goal tolerance. So I was just kind of talking generally where I don't know if you, so if you can still see like, um, for the I don't remember where I think the goal tolerance parameter is in the global cost map, but whenever there's like a
I
tolerance
don't think
parameter,
so because the global cost map is in charge of like things about the map. So I might be wrong, but maybe the goal tolerance, because I don't remember either. It's got to be in the DW planner or the move base params, maybe.
so this is one of the tolerances that so the global
There we go.
the default
Global
tolerance, so a
planner.
tolerance on the goal point for the planner.
So
So
you
like I
think
so
uh,
this was just one example of like a parameter that I was messing around with where I if I had to look it up, but I think that this is um like how close the like because the robot starts off when it does its global planner, it starts off doing the entire trajectory. And then I don't remember exactly, I just remember this being like something that I messed around with. And if I made it smaller, more precise, there would be a lot more oscillations. And sometimes like when I would look in like RViz, for example, there would be like, if you really made things like in the, like there's another example of it where you have, this difference between path trajectory, path distance bias, and goal distance bias. And if you kind of mess around with these like scoring parameters too, like you can notice like if you make things like really precise in some instances, like the path becomes like you know in machine learning when you overfit, you kind of have like a really like jagged like it really goes like to all the points type of thing, and then
no,
like
but I
it's much less
understand
of a
what you're
smooth
saying.
it's much less of a smooth path. And there was a lot of things like that where the path would become like kind of weird. Like if it was really precise, it would become like kind of jagged and it would go like kind of like weird like that. And um like some of the things that I was just talking about before, like I don't know if there's a particular threshold, but like um um I didn't really come up with like a great explanation for like the overshoot that it was doing. I only really noticed that kind of overshoot behavior when I really tried to because I was getting frustrated because like especially for like the pedestrian thing where it wasn't getting close enough to the crosswalk, that I would try to increase the goal tolerance and or try to find like things related to um that sort of precision. I don't know if that default tolerance there is the only parameter, but this was like one of the big ones that did um, have some improvement. And when I really did increase that, it would come out and start to like do like these like weird sort of um, soup I have like footage of um, it going and like I mean I don't know if it's worth showing, but like there were other examples where when I went to corner one, it would kind of do like that similar sort of like super like it would like almost like there was other cases where it would like go and stop at corner one, and then it would kind of like it looked like it was stopped, and then it would kind of like start moving again, and then I don't know, just a lot of weird things like that. And
Right. So the what I'm trying to get at, let me
uh,
rephrase my question. Um, how did you know that the robot was correctly localized? Because I think that it was the issue, right? Because what did you do to localize the robot in the simulation?
I didn't do it like there wasn't any real differences in terms of the
Except
simulation
for the
versus the
map,
lab.
correct? Did
Oh,
you
oh yeah,
make
the
different maps? That's the
oh the map, yeah. Oh, sorry. Oh yeah, if that's what you were trying to get at. Yeah,
yes,
that was something that I did come in to an issue with in I did make two different maps in the lab and the simulation, and I tried to keep tabs on it to make sure that I was switching back and forth between the two. And one of the things that I did notice in the lab too is that for some reason there was like well, in the lab, for example, they have like those the obstacles in the center, they're not
exactly,
static,
exactly. They
and you
move
can like
around, and this
yeah,
will affect how it's
yeah,
localized. So I wouldn't see it as an error that you think it's like frustrating that it's not gonna get there, because even for precise things like, for example, auto charging and things like that, you wouldn't use navigation because of this reason, because it's not precise because enough, because it depends on how you're localizing it. So in the real robot, there's noise, the obstacles move around. There's no extra pedestrian there that gives you an edge. It's kind of a symmetric map. So it's going to have a hard time localizing itself perfectly, not perfectly, but as good as in the simulation, right? And you could see this by looking at the AMCL particles that are being um, published in RViz. You could see it probably. And um, so that would for me, that's what explains this difference that you were talking about. Um,
okay,
and the goal tolerance, it just means that if you make it real tight, it's going to be real hard for the planner to get the robot exactly there. And you were talking about some replannings that it was almost there and then move it around. That was probably the inflation radius being too big, and it gets too close to it and it can't get specifically there because you set a tolerance that is too tight for that. So then it tries again. It's a recovery behavior that you
yeah.
add in the move base package. Okay, let me ask you one more question. That just, I heard you say that the, can you explain the difference between the map server and the AMCL nodes?
Um, I mean, yeah, there's like different levels of that, but like I know that like the AMCL node is more about
Like the
uh
simplest level of
like
explaining it.
I if I understand correct, like the AMCL is more kind of like it has like a particle filter or something like that, and like it it's like responsible for like reading from the lasers and then converting that into like the OGM or something, and then the
What's
map
the
server,
OGM?
the occupancy grid map. It's like the thing that it's basically the map that the robot reads from, and then the map server will. Only thing that I remember off the top of my head from the map server is that that's how like you allow like the robot, if the robot wants to read from, like if the robot wants to utilize the map that it just saved, you start the map server, and the map
Yeah, that
server
was my
will.
question. So, yes, basically, AMCL is in charge of localizing the robot, like using the laser and configuration files and TFs and things like that to tell you where the robot is. And the map server is literally only used to provide an image, a PGM, I think it's, to the raw system. So then localization can use it. I asked this because maybe it's because you were going fast. You talked about the AMCL node providing the map, and I just want to uh, tell you
Okay.
so you keep it separate in your mind, because once problems occur, you don't really know which way to attack. So yes, that's why I asked that. And all right, well, other than that, it looks like you've done a lot of testing, which is important, and you expressed a concern that you want to know what every parameter means, right? Uh, I don't know
Yeah.
what every parameter is. I would bet
Okay.
my house that 95% of people that use AMCL and move base don't really know. They just start off a template and then change the parameters that they need to change once they encounter a problem, right?
Okay.
So you're doing what you should do, which is focus on the couple parameters that you um, need to change. For example, I see one stop time buffer. I mean, that's probably the time that it would stop between replannings or something like that. And there's a comment right there that explains
Oh,
to
I
you.
see.
But you don't want to, I mean, I've never touched it because I don't need to, right? Because it works well enough without it.
Yeah.
Considering I don't want it to be exactly precise and things like that. And that's when you can jump into improving this, like using a Kalman filter for localizing, or you know, go into making it go real slow. That's another way to make it converge quicker. And but yeah, that's the main way to do it. I would I would say that is the way to do it, and you did it right. And now you can look into, now that you have a working setup of a robot, you can expand it to whatever you want, based on the kind of robot that you have, the precision that you need it to be, the navigation, things like that. But I think I'm out of questions. Other than that, it looks
Okay.
like I was gonna ask you, why do you have only a client, action client node and no server? But you answered it yourself, saying that move base is an action server basically, and you can actually just send an action through the command line if you have move base running, and it will listen to it. So that's another question I had. Other than that, it's very clear, and I'm pretty satisfied with looking at how the results came out. What was your takeaway with this? What would you want to do with this, and how would you like to move forward with, applying some autonomous navigation to a robot?
Yeah. I guess we kind of went over a little bit some of the takeaway, and I definitely like to like see more of like what is the real world net like, because I think that this is still a pretty, even though it is kind of, it works well, but I think it's still a pretty simple navigation, like a starting point anyways. But
What would be a
like definitely look,
complicated navigation?
was that
What
what?
would be the complicated version of this?
I don't, yeah, so I know that there's like I don't know the extents of like what is more complicated, but like for example, like I know that there's like sensor fusion, and that's one of the courses that you guys offer. And um I've also seen like recently like using like doing SLAM with like reinforcement learning.
Oh, okay.
um
I haven't actually
I
done that.
and I know that like I've looked briefly at some of the probabilistic robots literature or like textbook or something, and I know that there's like different versions of like there's like for common filters, for example, like there's limitations to the common, like you could do like EKF common, like there's different sort of common filter algorithms and different approaches to going. Yeah, I'm not, I know that there's more to SLAM, and I don't the textbook that you guys mentioned is the probabilistic robotics by Sebastian Thrun, and he goes through a much more detailed take on some of these algorithms. And um, I so I don't know what it is. I would like definitely I would think I would try to look at seeing better understanding a little bit more sensor fusion, or just looking at some of the more detailed algorithms in like the textbook and seeing what they specifically do and how I could try to adopt some of that into here.
Okay, yeah. So
Yeah,
there's just one suggestion I have for you, and is to also separate what the whole area of localization is and what navigation is. So you're talking a
yeah,
lot about SLAM. That's only to tell you where the robot is. That's not going to tell you anything. That's not going to make the robot move anywhere, right?
oh, I see. Yeah,
So
yeah,
you can expand this. You could make it really precise. You could do the extended Kalman filter, like it's of course we have offering in here in the construct, where you can just shove in the IMU to make it better. If you have a point cloud, you can use that, and things like that. But that's only to improve the localization, which at the end of the day is kind of the most important thing, because if you exactly know where you are, then the planner for the move base server, which is what actually sends out the command velocities, it'll be a lot easier, and you won't have to, do a lot of things in the move base area. And I mean, for example, for my applications and what I've worked on with move base and the nav2 stack, which is for ROS2, I mean, I don't really touch the path planning part of it, the
I see.
what moves the robot. I know there's like the DWA robot, which is good for differential robots, and then there's the TEB local planner, which is real good for following trajectories for like a car-like robot. But again, that distinction, especially for debugging and when things go wrong, for knowing which area you have to tackle, that's why I'm mentioning it.
Okay.
All right, and other than that, it's a great project, Mike. Do you mind stopping sharing your screen here so we can say goodbye here? All right. Well, yeah. Again, Mike, congratulations. Now you have a working system that you can pretty much, if you have a robot, any type of robot that's differential drive, you can use this and it will definitely do its thing. And then you have to identify what's the issue. Is this a really bad map? Is this not localizing correctly? Do I need to disperse the AMCL particles once in a while because it seems like it gets lost? Things like that, which is related to like a case by case situation, right? But I mean, other than that, for everyone else that's watching, since we're wrapping up, this is what you can do with if you take the ROS navigation in 5 days. You can set up autonomous navigation for your robot, like Mike did here. And yeah, so if you're trying to learn some robotics, this is a good place to start. So thank you very much, Mike, and I hope we see you soon for another course.
All right. Thank you very much.
All right, guys. We'll see you later, and remember to keep pushing your ROS learning. Bye-bye. All right, that's it.